Hey guys, can you hear me?
Yes.
Okay, we've got a little bit of time here before we get started. Are there any questions or comments?
Yes.
Yep.
Hello, Professor. So I was trying to finish, or at least attempt to finish the homework problems that are due this week, and I realize I don't understand, except perhaps the last question, how to do any of them, because I don't think we covered martingales yet.
Let's just have a look.
Okay.
Mm, mm, so- yeah, we're going to talk about this tonight. We're going to talk about, so here you need to know what a martingale is, and here you need to find these backward induction functions. This is tonight's lecture.
So then would you extend this period of homework again or not?
Yeah, I mean, you guys can have a few more days to do it. This is not a big deal.
Okay, thank you.
Yep. Are there other questions or comments? Okay, then I'll be back in a few minutes. Okay, I think it's time to get started. So there's another question about homework 5. Yeah, so we will push the homework 5 a few days back so that you have more time to work on it. You'll need martingales from tonight's lecture to solve that. So I'll update the Canvas site either tonight or tomorrow. Okay, so let's get started. So where are we at? So where we're at is working with these conditional expectations. So we're looking at a random variable. We're looking at a random variable which is f measurable, and then we're having a sigma algebra that is inside f, and we've been talking quite a bit about the conditional expectation, which is going to be another random variable, and this is going to be g measurable. And it's going to satisfy this partial averaging property that says that when you integrate x over sets inside the sigma algebra G, you're going to get the same thing as when I integrate the conditional expectation. For all sets inside G. That's the definition, right? And we talked about properties last time. In general, there's no formula for it, but so there is a lemma. There's a lemma, and this is called the independence lemma. It actually appears in both our textbooks. So you can find it a couple of places. So if you look at the thin one, the first book, you flip over to the back, there'll be an entry for the independence lemma, and it's this one here. So independence. This is so I'll write it up here. You can also find a version of it in the thicker book. And what it says is, so you take two random variables, x and y, and we're going to have them to be independent. You take a function, from R2 to say R, which satisfies either f of x comma y is positive, or it satisfies that the expectation of the absolute value of x of f of x comma y is finite. It satisfies either f is positive or you get integrability. Then you can compute a conditional expectation. You can compute a conditional expectation of so I have independence. So what you're going to do is you're going to take f of x comma y, and then you're going to condition on, say, y. This conditional expectation can be computed, and there is a formula for this one. This one here has the form. It's an expectation which is unconditional, and what you do is you take the random variable y outside, you replace y by a dummy, and we call it for a. Right, so this is going to be an unconditional expectation, so those are the ones we're used to. And then you replace a with y. So the textbook writes this slightly different. The way that the textbook writes it is by saying I have a function g of a, which is this expectation over here. Nothing conditional about it. So the textbooks define this function. A here's a dummy, it runs somewhere in R. And then it says that the conditional expectation of f of x comma y given y can be computed as g composed with y. So my preference is to write it like this. You compute an expectation where you have replaced the y measurable, replace y, the thing that you condition on, by a dummy, and then you perform an unconditional expectation. You compute it as a function of a, and when you're done with it, you replace a with y. This can look pretty abstract, so let me show you how this actually works in a specific example. Let's do a specific example so we can see what all these pieces are like. This is an old exam question. So you take x and y, the standard normals, and you're going to make the assumption that they're independent. Then what you want to know is, I take an exponential of, say, a constant b, and then x times y given y. I want to know what this is. So here I have my function, my f of x and y. This is equal to e to the b x times y. So in this particular case, I have a positive function. So I'm in the first case. So then I can use the formula. And the formula says that I can write this here. This conditional expectation can be written as an expectation, where what I do is I replace the random variable that I condition on here, y, by a dummy. Let's call it dummy for a. And I perform this unconditional expectation, and when I'm done with it, I replace a with y. But we know the moment generating function for a standard normal. We've had that one a number of times, etx. This was equal to e to the, does anybody remember?
1/2 t squared.
Yes. So if I use that up here, I'll get, like I apply this formula for t equal to ab. So I'll get e, b, x, a. This is equal to e to the 1/2 a squared b squared. So now I'm done computing. There's no more expectation to be found, and we get that the conditional expectation of e, b, x, y given y, this is this e to the 1/2 b squared, and then the random variable y squared. Okay. So that's what this formula here means. It compute this expectation. When you're done computing it, you replace a with the random variable y, and here, done computing it, you replace a with y. And so this can be used, for example, to study this particular question here, was part of a longer list of questions. So you can use this. You can use this conditional expectation to decide when, if I am to look at something like e to the bx y, when is this stuff finite? bringing this issue up because I was working a little bit on your homework, the next set. And let me just show you where something like this comes up. So let me share my screen so we can see it. There's a problem here on the next homework, problem number 2. And so here what you have is you have x and y, you have 2 independent random variables, and you're interested in changing the measure. Here's a random negative derivative, and you can see there's an expectation down here. And this expectation involves the product of x and y. So it would be nice to know, when is this expectation you have downstairs actually finite? Right? Because if this is infinite, I'm not going to get something that is strictly positive. Right? If this is infinite, I'm going to get 0 again. So this calculation we're doing now is part of your homework, number 6. So let me show you how to determine. So here I call it B in the homework. So B is theta in homework 6. So how will one determine that? Well, we'll use iterated expectations. So I know that this expectation out here have this property that the conditional expectation is unbiased. So if I plug in a conditional expectation in the middle and take expectation of that, I'm going to get exactly the expectation of the original random variable. And this is iterated expectations. This is what we called unbiasedness. And now what I have in here is what I computed. So I'm left here with an expectation of the last line. The last line on page 2, so this is page 3. So we have this we have this conditional expectation is that mess over here, and we're going to plug it in here. E to the 1/2 b squared y squared. So when is that finite? When is that finite? You can see what we're computing over here. This is the moment generating function for x times y. This here is the moment generating function. For x times y. And so we're asking, when is the moment generating function finite? We're not necessarily asking for what it's equal to, but we'll settle for now for what b's will give me that this expectation is finite. And so this is along some of the questions that you saw in the homework, one of the first ones. Well, the way to do it is you have to write out, you have to connect what the expectation, if you're integrating over omegas, you can integrate over the codomain of y, so you can write this here as an integral using y's density. So this is e to the 1/2 b squared y squared times the density 1/√2 pi e to the minus 1/2 y squared dy. When is an integral like this one finite? Well, very often there's a critical case. What's the critical case?
Wasn't it like -1 in the homework?
-1 in the homework. I don't think you've seen this. Have you seen this problem here in the homework yet?
Oh, I thought you were referring to the first homework, so I must.
I don't think we had this, but so it's similar to what you were doing in the first homework. Right, there was a different function you were studying in the first homework. But you have to look at the function in here. What's the critical case? What is the critical values for b?
I think like once it's negative, it should be finite. But wait, but b is never negative because it's a square.
But b can be negative.
No, b b squared can be.
B squared, yeah, b squared is not going to be negative. So there's something that is critical with b squared. What is the critical case for b squared?
0?
Well, if b is 0, then you get an exponential of 0, that's 1. So that's going to be finite. And that's not the critical case. Look at the function. When do you get something special in here?
When b is infinity?
When b is infinity, we don't like that, right? B here is a real number. Like I'm mapping b into this. B here is a real number.
Someone said 1 in the chat. I think
Okay, that's right. So the critical case is b equal to 1. What happens when b squared is equal to 1?
you get e to the 0,
Which is equal to
1.
Oh, so I'm seeing a question in here, √2 over y. No. There is no y dependence here. B does not depend on little y at all. B has no dependence on little y. Little y here doesn't have any meaning. I could write y here. I could change this up and I could write x here. And I could integrate with respect to x. I could write, if I don't like x, I could write Rutgers squared. I can write Rutgers squared here. And I can write d Rutgers. There is nothing special about that little y. That b here can in no way depend upon little y. B is just a dummy. Then we're looking at a function mapping b into this. And there's no little y anywhere to be found up here. The critical case is b squared equal to 1, because in that case, what happens is that we're going to get exponential of 0. So in this critical case, do we have finiteness or do we not have finiteness? Well, we were integrating 1 over r. When I integrate 1 over r, what do I get?
Infinity.
So the critical case, it does not give us that. So what's the condition on b here? The condition on b is, should b squared be less than or bigger than 1 to get finiteness?
Will it be between like -1 and 1 strictly?
So b squared is strictly. So that's the condition. So the moment generating function for the random variable x times y is finite, provided that the parameter is strictly between -1 and 1. So this was one example of how one could use. This is one example of how one could use the independence limit to compute a conditional expectation, then use that conditional expectation to determine whether or not a given moment generating function will be finite. So this independence limit, this is something that is going to play. It plays a pretty big role in both this course, and it also is going to play. It's also going to play a role when we move in when we move away from discrete time and into the second half of the course. So what I want to do now is I want to get back to doing derivative pricing. Now we have the theory for conditional expectations. We've seen some of its properties. We've seen this independence lemma. I want to try to use the rest of tonight's lecture on applying this material to the multi-period binomial model. So this is going to tie it back now into the material that we had in the very beginning. So the multi-period binomial model. So what we do is the starting point is these Bernoullis. So you're going to start out with either a finite number or an infinite number. These are IID coin flips. So there are two values for these size. It can either be U or it can be D. There's a probability P for going up here and 1 minus P for going down here. So that's the starting point, and then from here on we create the bank. The bank has the formula that we started out, say at 1, and then we're going to say that at say time n plus 1, the definition is that you take the previous bank value and you multiply it by 1 plus r. And of course you can iterate here. You can say that this is Sn minus 1, and then you get 1 plus r squared. You can keep doing this, and then ultimately you end up with 1 plus r to the n plus 1, if you so desire. That was the bank. So again, there's nothing random about this. There's no randomness. But that's the same as in the one period binomial model. So there was also no randomness in the bank there. So you'll do the stock then. So the stock here, you start out some positive value of the stock, and then you define the stock price at time n plus 1. It's again defined recursively. It's very similar to the formula here. You take the previous one, and then you bring into play the Bernoullis. So Sn times psi n plus 1. And of course, you can iterate it like before. You'll end up with S0, and then it'll be psi 1, psi 2 times psi n plus 1. So the stock price at time n plus 1 is going to be the product of all these coin flips that are coming out. So we can illustrate this on the picture. We can start out here with the initial value, something positive. We can go up and down. and so on. And now we are equipped to study and analyze this model because we have conditional expectations, so we need some sigma algebras. So we're going to define a sequence of sigma algebras. We're going to define Fn. It's going to be the sigma algebra that makes the first in stock prices measurable. This here is the smallest sigma algebra, making Sk measurable for k running between 0 and n. But of course, if I look at what the definition of S is, I can equally well say that this here is the same as the sigma algebra that is being generated by the first n point flips. Right, so that's the smallest sigma algebra that makes the first n Bernoulli random variables measurable. So this is called the filtration. This is Fn. This is an example. This is an example of a filtration. And the reason it is a filtration is because you have this increasing property that Fn is inside Fn plus 1. And we now have, so we can, this is going to be our flow, this is going to be this Fn structure, this sequence of sigma algebras. This is going to model, our flow of information. That's how we're going to be thinking about the sigma algebra. So we are thinking about these indices as being time. So Fn encodes the information that we have available at time n when we decide on how many stocks to buy or sell. And so when we make a decision at time n plus 1, we also have observed the stock price at time n plus 1, so we know more, so we can make better informed decisions at later times simply because we have observed more stock prices. Let's try to compute some conditional expectations and see how it typically works. This here is a multiplicative. You see this is the previous stock price times these Bernoullis, these coin flips. This here is multiplicative. Alternatively, we could have put in a plus here. So we could have had the previous stock price plus the outcome of this Bernoulli. That could have been our next stock price. So then we would have gotten, there would also have been a binomial model, but it would have been an additive binomial model. Here it's a multiplicative structure. Okay, just something to keep in mind when we start doing calculations, because we're going to be coming back to this particular definition quite often. And so just remember, to get the next stock price, you take the previous one times the outcome of the Bernoulli. So that's what you do in a multiplicative binomial model. So let's try to compute. So if we want to try to compute something like an expectation, say, of the stock price at time n plus 1, given Fn, this is what we've been working so hard to become able to do. So let's try to do it. Let's warm up with this one. So how would we do it? Well, we'll replace Sn plus 1 with the definition that we just had. The multiplicative rule was Sn, then the coin flip, and then condition. So then what do we do? Well, now it's time to use some of the properties that we have discussed related to conditional expectations. So we will have Sn here, and then we have a product. Right, and Sn, this is already measurable with respect to Fm, because Fn makes all the previous stock prices, including the nth one, measurable. So here, Sn is already known, it's already observed by an investor that has access to the information in Fn. So we can pull him outside, and then we're left with the conditional expectation of the n plus 1th coin flip given the previous coin flips. But then we use the assumption that I have IID coin flips, so they're independent of each other. Okay, if they're independent of each other, that means that here I have information about the first n coin flips. And I'm trying to estimate the n plus 1th coin flip given information about the previous n coin flips. But you're independent, so we'll just get the unconditional expectation. We just get the unconditional expectation. That was because we had independence. So the first one, here we're using that Sn is Fn measurable. Here we're using that psi n plus 1 is independent of psi 1, psi 2, all the way up to psi n. And then we just ask to compute an expectation of a Bernoulli. This is Sn p times u plus 1 minus p times d. The calculation we see here is a very common calculation to see in these Bernoulli models. When you have this product structure, you'll see the product, you'll end up taking one thing outside, and then you'll use independence to get rid of the rest. So we'll see this in many, many different contexts. Here we computed the expectation under P. But we have also worked with these risk neutral measures. So we could also try to compute the expectation under the risk neutral measure. So let's try this out. So recall, we have these risk neutral measures. We call this risk neutral measure. Right, so here we're going to have that these guys, they're going to be IID again, and you'll go up to U and D, but here we'll have P tilde, and here we have 1 minus P tilde, and we have P tilde has a formula, which I always forget. To make sure. P tilde is 1 plus R minus D divided by U minus D. So let's try this one out. I want to compute exactly the same thing, just under a different measure. Let me try to do that. Expectation, now under the tilde probabilities of Sn plus 1 given Fn. So we'll proceed as before. Insert the definition of Sn plus 1. This is Sn times psi n plus 1. given if n. So then we still have that Sn is measurable, so you can go outside. And we'll still have that we can just use independence of psi n plus 1 and Fn. So just get psi n plus 1 here. And then we'll get, as before, but with the p tilde probabilities, this will be p tilde u plus 1 minus p tilde d. Okay, so that looks the same and pretty boring, but it doesn't take much to make it interesting. If you now divide by 1 plus r, if you now divide by 1 plus r, we're going to get that Sn plus 1 given if n. This will be Sn divided by 1 plus r p tilde u plus 1 minus p tilde d. Can we get something interesting here? Well, let's try it out. I'll get Sn 1 plus r. I'll get p tilde times u minus d. And then I'll get plus d. Now if I take p tilde from up here, we can now see something interesting happening. P tilde from up here, plug him in here, what will we get? The u minus d will cancel out. I'll get minus d, I'll get plus d, I get 1 plus r divided by 1 plus r. When I do this, I'm going to get Sn. Another thing that we have talked about, also recall when we discussed these error diverse securities. Recall when we discussed error diverse securities, we used these discounted prices. We use discounted prices, so we would look at Sn tilde. This was Sn divided by Sn0. We would look at Sn tilde, say 0. That's easy because this is Sn0 divided by Sn0. This is a 1. And then the wealth, Xn tilde, this would be you need to know it only. Okay, so we're going to use that later. So if I cast everything in terms of the discounted prices, maybe I can write out what this one here is. This was Sn divided by 1 plus r to the n. So if I look at the conditional expectation up here, I get Sn tilde given Fn. This would be Sn plus 1 divided by 1 plus r n plus 1 given Fn. And I want to get to use this formula. And I can do that because I can pull out 1 plus r to the nth. That will leave me with Sn plus 1 divided by 1 plus r, which is what I have out here. And that calculation produced Sn. Right. So this is times Sn. And this was exactly Sn tilde. There was a question in the chat. is this the same as the initial derivative price? We're not pricing derivatives yet. We're not pricing derivatives yet. Right now, we're basically just playing around in the binomial model. We're just playing around in the binomial model. We're just computing conditional expectations. So far we've succeeded in computing how many conditional expectations. So we computed this one, that was one. We tried to get the hang of how to compute these conditional expectations. Then we computed this one, that was another one. And now finally we computed this one, and that was that one. So here, the one when you have the tilde probabilities, you have the discounted stock price, you see that the conditional expectation of the future stock price discounted is just equal to the first one. So this is a special property. And it has a fancy name. This is called the Martingale property. This is called the Martingale property. And this is why the risk neutral measure is also called the Martingale measure. So let me write down the formal definition of the Martingale. Maybe before I plow into the Martingale definition, do you have any questions on how to compute these conditional expectations that we've been doing on the last few slides?
Hi, Professor. Does one have to check the properties before, or is it the assumption that the properties hold when we solve these problems?
I'm not sure I can follow. The assumptions that we have to work under is
Like the one we derived to make sure that it actually works and matches our prior definitions of conditional expectations. That's what I mean if we have to check in for these as well.
are you talking about being integrable?
Now, you know, the way we defined the conditional expectation in this class was slightly different from a standard probability class. That's why I'm asking if we need to assume those assumptions are right from the derivation to solve these, or we have to check in some of those assumptions.
Okay, now, so what we're doing here is we're using properties. We're using properties of the general conditional expectation that the general conditional expectation that we've been working with. And one of the properties that I think we talked about last time is that you can pull out, if you have a product, you can pull out what's measurable. If you have something that is independent, then you can drop the conditional expectation and so on.
Okay, thank you.
This here is this general notion that we've been talking about throughout. This conditional expectation here, this has that property that when I integrate Sn plus 1 over sets in Fn, I get the same as when I integrate this quantity here over those sets. Yep. We're going to be working exclusively with this general notion of conditional expectation. And we're going to be working with all the properties that we have discussed, and in a little bit we're going to be using this independence lemma, and that's the same thing. That independence lemma is about how to actually compute this general conditional expectation if you have some independence in the problem, which is what we have here. Okay, so let me talk about martingales. So a stochastic process is a definition. So this is a definition. Let me use the word, let me use M. This is a martingale. But you take a sequence of random variables and you talk about a martingale property if, and then there are three conditions. The first one is that Mn is going to be Fn measurable. And this is for all n. This here is also called adapted. It just means that when I take, just to speak of a martingale, I need to have a sequence of random variables. So a sequence of random variables, this is, I cannot talk about one random variable being a martingale. This is impossible. I need a sequence of random variables, and I also need a sequence of sigma algebras. And so Mn must be Fn measurable. The second one is Mn has to be integrable. So when I integrate, I got to be finite. And the third one, I need this one so I can talk about the conditional expectation in the third property. If I take Mn plus 1, I condition on Fn, I'm just going to get Mn. And this is also true for all n. So I have a stochastic process, I have a sequence of random variables, I have a sequence of filtrations. This is called a martingale if I have these properties. Okay. We just saw an example here. This guy here, the discounted stock price, this is a martingale in the binomial model. The prototype, a very large class of examples of martingales, they are given by this example here. It's not all of them. There are martingales that are not in this category, but nonetheless, these martingales they call Livy martingales. And so what you do is take a random variable. I need it to be integrable. I always need, this integrability is not going to come for free. It has to come from somewhere. So take a random variable. I require that it's integrable. And then if I define Mn to be a conditional expectation, this object here is the prototype of a martingale. So go over it again. You give me any random variable that's integrable. If I form this family of conditional expectations, I get a martingale. For how useful this is in the weeks to come, the proof is deceivingly simple. The first step is I have to be measurable, but this is okay because it's a conditional expectation, and one of the two properties of a conditional expectation is that you're measurable with respect to what you're conditioned on, so that's okay. The second property is that I have to be integrable. It also has to be integrable. So if I look at the conditional expectation, so I need to look at the absolute value of Mn, and I need to prove that this is finite. Okay, so the first thing I can do is I can take the absolute value of the conditional expectation. So I can do that. So then what do we need to do? We have the absolute value. This here is my absolute value of x. There's convexity here because if I take 2 points, and I draw a straight line, then all the points on the red curve are at or above the blue curve. So this is convex. So then there's something called Jensen's inequality. Jensen's inequality says that if I move the absolute value inside an expectation, I'm going to get something that's bigger. Okay, so if I move the absolute value in here, I'm going to get something that is bigger. So I'm hoping that you guys have seen Jensen's inequality somewhere. Jensen's inequality, so you take phi convex. I need it to be integrable. I need phi of x to be integrable. Then the Jensen inequality that I'm hoping that you guys have seen is that if I want to compute the conditional expectation of just the expectation, say, of x, I can pull this function outside and take an expectation inside. So if I have phi is inside, which one is biggest, when phi is inside or when phi is outside?
When it's inside?
Yes. Okay, so here's a trick to remember. So I can see not all of you have seen Jensen's inequality before. So the trick to remember Jensen is you're going to do a test. You're going to test with phi of x, this being the square function. Right, this here is convex, this is the square. Right, so if you have seen when you've discussed convex functions somewhere in your past, if you've seen that a function is convex if and only if its second derivative is, what is it, positive? Yeah, if and only if the second derivative is non-negative, then you can do that test on this one. You can't do that in general because it's not given that the function is differentiable. Like the absolute value is not differentiable at 0. The hockey sticks that we have talked about, they're put in the call options, like this one. This is also going to be convex. This is the call. The put is also convex, but it's not smooth. There are these points where there are kinks. So then you cannot use that trick. And out of paper. This was page 9. Okay, so if you can't remember what way to put Jensen's inequality, so you know we have a convex function. So what I propose to do is just to test it out with a square function, because you know that the variance of a random variable is non-negative, and you also know that the expectation of x squared minus the expectation of x squared, that difference is going to give you the variance. So then you can move this term here to the other side, and you can see you get something that is bigger when the square is inside than when it's outside. This is just an easy way to remember or to figure out what way Jensen's inequality goes. You get something that is bigger when you sit inside. If you've never seen Jensen's inequality before, so that's a little problematic, but you have seen versions of it. Like if you look at one of your homeworks, you had an exercise, or maybe we did it in class, we would do something like conditional expectation of x given y. This was like a row y. When you had joint normality and you had a correlation with rho. And then you also had a question in the homework where you were asked to compute e to the x given y. You did that one. I forget it was the last homework or 2 homeworks ago, but and so you see here there's an exponential function, and the exponential function is also going to be convex. So here I have the exponential function inside. So we have pulled the exponential function outside, so I'll get e to the conditional expectation of x given y. Then I'll use that I'm biggest when I'm inside. So I'll get this. And so I'll get that this here is e to the row y by what we did in class. So you know from the get-go that this conditional expectation that you're trying to compute, it is bounded from below by this number, by Jensen. This one here is Jensen. And what you actually found the expression for the conditional expectation. So you should do a sanity check. Make sure it doesn't violate Jensen. And if I remember the answer correctly, it's something like, what is it, plus 1/2? Does anybody remember? 1 minus rho squared, is that right? So let's just do a sanity check. Is it really true that what I have here dominates what I have here? So a sanity check. Do we really have that e rho y plus 1/2 1 minus rho squared? Does it really dominate e rho y? Because if it doesn't, then there's a mistake somewhere. And since Jensen's inequality has been around for a long time, it's probably not in Jensen's inequality. It's more likely in this calculation here that there's a problem. So say that, for instance, you've gotten a minus sign here. Say that you've gotten a minus sign here. Would it still work? If I put a minus sign here, would it still work? This one here is the same thing as saying e to the 1/2 rho 1 minus rho squared is bigger than 1. Is that true?
Do we know what rho is again? It was the very
The correlation coefficient.
oh,
Where do correlation coefficients live?
it's probably less than 1.
It is squared, right?
Yeah.
Yeah. So this is true. But you see, had you gone through this exercise and somewhere in your calculations, you would have messed up and you would have put a minus sign here. This happens to the best of us. Then you would come down here and then you would have a minus sign here. And this would be false. It's not true that if I put a minus sign here, I'm bigger than 1. Right? So that would be a mistake, and this is something you can check. Hey guys, good night, yo. Good night. All right.
Why can't I wait?
Because I'm trying to teach, guys. Okay. Good night, guys. All right, let's get back to this. So say that you had done this calculation and you would have gotten a minus sign here. You do the sanity check and you come down to saying, okay, so I have a minus sign here, it should be bigger than 1. This is not possible because the exponential of something negative, this is less than 1. So then you would violate Jensen. So that means that there's a mistake somewhere in your calculation. Go back, see if you can find a mistake, change the sign and come back and make sure that the sanity check pans out. So that's Jensen's inequality. Here it's stated for the unconditional ones. There's a conditional version of it too. If I have phi of x given g, this dominates phi of the conditional expectation of x given g. That's Jensen's inequality. So what I'm using now is in that last step here. In that last step, I'm pulling the absolute value inside the conditional expectation. I get something that's bigger. And then the final step is again to use the expectation of the conditional expectation. It's just the unconditional expectation of A, right? This is this unbiasedness of the conditional expectation that we talked about today, and we also talked about last time. And this is finite. Right? That's finite. That's finite by assumption. So now I established properties 1 and 2. I'm still missing the last one. The last property.
Oh, Professor, for the last thing you just did, was it because of the iterated?
Yes.
Okay.
Right. That the expectation of a conditional expectation is the same thing as the unconditional expectation.
Okay.
The third and final property, this is again iterated expectations, that's what just mentioned. We will I have some paper. Paper. We need to establish the last property. We need to establish the third and final property that I'll do the conditional expectation and I get the right thing. So let me compute mn plus 1 given fn. I'll plug in what the definition is of mn plus 1. This was the conditional expectation of A given fn plus 1 given fn. So now we again have one of these conditional, we have two conditional expectations sitting next to each other. We have fn, we have fn plus 1. We need to remember when I have two conditional expectations next to each other, which one wins? Well, the one that wins is the smallest one. That's going to be fn. And so this is my amen. So that's the proof of why these Libby martingales, they are indeed martingales. And it's quite important to stress that this works for all random variables A. Give me something that's integrable, this is always a martingale. And so there are a couple of places there you'll see this in two places. So the first one is you will see it in these red and Nicodim derivative processes. So let me just show you. So if you look in, it's also in both books, but if you flip through, the table of contents, you'll see where's the table of contents. You'll see down here in chapter 3, you'll see there's the Radon-Nicodim derivative process. And so there are a number of pages devoted to this object, and here's what it is in a nutshell. You take your dq/p and your condition, and you call this object with z. This is now a martingale.
Because the Radon-Nicodim derivative is integrable?
Yeah, it has expectation 1, right?
Okay, so this is like Levy martingale.
Yes.
Okay.
This is a Libby martingale, right? So you'll see these Libby martingales in two places, maybe more, but at least these two places. So you see it here. Another place you'll see it is when it comes to derivative pricing. So for a function, say f Um, you'll see it. You'll see it when you compose, and then you have a binomial model. So you have Sn plus 1 is equal to Sn psi n plus 1. And you have these Bernoullis, the IID, they go to U and D. You'll see it over here when you compute a conditional expectation of, say, a payoff at time capital N given f little n. So this here is for n equals 0, 1, 2, up to n. So you'll see it there. And there's a warning too. Very often you will also need to compute, say, something like this. But then it's kind of messed up because inside here there's a 1 plus r, and then you'll have something like n minus little n. This is something that appears from time to time, and you're being asked to compute this. So now the problem you're facing is that there are too many little n's. There's a little n here, and there's a little n here. This one here is not a martingale, right? So these two here, they are. This one here is not, and the reason that they're not is because this random variable that you have inside the conditional expectation depends upon little n. So when we defined m, there's no little n dependence on a here. There's nowhere you see an n around a. And here we have this little n dependence inside, and that's a no-no. It doesn't work. Are there any questions or comments on this? So now we have a very, very large class of martingales. Have all these Leview martingales. Are there any questions about this?
Oh, I have one thing.
Yeah.
Remember when you said like the smaller term wins with the filtration?
Yeah.
The two. Can you explain that more explicitly again?
So here what we're using is we're using iterated expectations. So we had, I think when you wrote down the properties, we had like an H inside a G. Mm-hmm. So what I did was you conditioned first the random variable on say G, and then you condition on H. And then the claim is that this here is equal to X given the small one. You could ask yourself, sometimes when stuff like this comes up, you can ask yourself, like, what else could it be? You could think that maybe I should put G here, right? It's either going to be F, it's either going to be G or H, right? So which one should it be? What happens if you pretend that this should be a G?
Well, it kind of begs the question, where did the H go?
So which one is biggest?
G is bigger.
G is bigger, right?
Yeah.
So then if you look at what you have up here, then this is going to be H measurable. Whereas if you had a G here, this is going to be G measurable. right? Just say that X,
Oh, so if you condition on H already, it doesn't make sense that it would be G measurable, which is bigger.
that's right.
Okay. Okay. I mean,
oh, go ahead.
I mean, like, is there a more like explicit
Of
way?
course, I mean, ultimately, this is stuff that you can prove. I'm just, if we go through the proof, I mean,
It's gonna be too long. Okay, I
it
got
would
you.
be way too long. We will not get very far. We will, yeah, we will not get very far. But of course, I mean, the proofs are in here, right? They are in the textbooks. Yeah. Can you go back to where I defined M? Yes, I can go back to where I defined M. I can do that. Yep. Here's M. M is the conditional expectation of A given given the filtration. Was there a question related to it? Oh, we have a few minutes left, so I can talk about what's coming next. But we don't have much time left tonight. But so what is going to come next is we're going to be pricing derivatives. We're going to be pricing derivatives. So we're given the payoff out here at the end. So over here we've been giving a function f of Sn. Right, this here is the derivatives payoff. So say we're looking at the payoff here, we're going to move it back to time n minus 1. That was the time point we have here. It's too slow. And we know how would one guess to do this? Well, you would probably want to compute. You probably want to compute something with a conditional expectation. Right, so the thing that you want to go from here to here is you would take the payoff, and then you would move it back a little bit, and then you would condition on the information that you have available at that prior step. And this here is going to be your wealth. This is going to be your wealth at time n minus 1. So what would it also be? Well, we'll try to work out what this conditional expectation is. And so we will go through the same motion as what we had done before. We have to take into account that this is now a function here. So we'll have f of s, it will be n minus 1, and then you have your psi. And you have this 1 over 1 plus r, you can go outside. And you have fn minus 1. And so now we can use the independence lemma, because I have these two guys are independent. I can use the independence lemma. I can use the independence lemma, and what it says is you freeze what is measurable, and then take average over the rest. And here the average over the rest is not too bad. This is p tilde f of Sn minus 1, and then psi, this can be either u or d. So p tilde for u, 1 minus p tilde for d, f of Sn minus 1 times d. So we got ourselves, this here is now a function of the random variable Sn minus 1. The wealth at time n minus 1 is a function of Sn minus 1, right? So we can call this thing here for Fn minus 1 of Sn minus 1. So how do we get the wealth at time n minus 2? Well, then you go one step further back. So now we're back to time n minus 2. So if we move back like that once, we can try to move back like that twice. So we'll get E tilde of F, but now it's going to be n minus 1 is n minus 1, 1 plus R, given Fn minus 1. This is going to be my wealth at time n minus 2. We go through the same motions again. This is going to be equal to 1 plus R, P tilde, basically copying what we have up there, but instead of F, you'll have F of n minus 1, and then it'll be Sn minus 2 U, plus 1 minus P tilde, Fn minus 1 Sn minus 2 D. And this will be my new function, Fn minus 2 of Sn minus 2. And so you keep doing this until you ultimately get the wealth at time 0. This is just when you move all the way out. They're going to be these two branches. So this here gives you a guess for ultimately what the wealth is at time 0. And now the question is, if I start out with this amount of money, can I find a way to invest in the stock such that when I follow that investment strategy all the way to the end, I'm going to get exactly the derivative payoff as my wealth at time capital N. So this is going to take me a while to flesh out, but the general idea is you create these functions here. You go back. You always start from the right and move to the left. So you at the end, when we're given this guy, so we have to work much harder to create this one. Then you work even harder to get this one. Then you get all the way out to here. We're going to get F0 of S0. So we're out of time for tonight, but that's where we'll start next time. We'll start next time by redoing these plots here, and then saying that if I can create this recursion, these functions recursively, I can use these functions to ultimately price derivatives by creating these replicating portfolios. So that's what we're going to be doing next time. Okay, we're almost out of time. Are there any more questions for tonight? So I will push the homework back a few days, just like last time. You should be good now on solving some of the questions on there, but you will probably need the lecture on Thursday to solve all of them. Okay, are there any questions before we call it night?
So what is the midterm again?
Second half of October.
Second half, okay. So we didn't have yet a definite date.
But it's not going to be a date, right? It's going to be a period.
Okay.
Right. I have in this class we have 30 students, and right, so this it's going to be blocked up into groups of some students, and then there'll be different days, and then you guys can sign up to when you would like to have it. I just want to make sure we get through the material before we put in the date. And I would like to have some slack there so that we can have some time before the midterms to have discussions about the material. We're falling a bit behind here. So setting a harsh date, I don't want to do that because I want to make sure we have enough time to get through the material. But it's going to be in the second half of October.
All right, thank you.
All right, any other questions? If not, then I'll remind you that we have office hours on Thursday morning, and then we have the lecture on Thursday night. Good night, guys.